Welcome back to our Chem 152 video series. In this video, we'll be balancing radioactive reaction equations. The goal for this problem will be to find the missing product. In order to balance this reaction, there are two things we need to check: the mass and the protons. If we look on the left side of this equation, we can see the mass, the upper number, is 238. We're going to set this equal to the mass on the right. We can see that the mass for helium is 4, and the mass for our missing product is not known, and we'll call that x. But you may be able to see that we can subtract 4 from both sides. This means that our mass is going to be x equals 238 minus 4. This gives us a mass of 234. We'll do the same thing with the protons. On the left, our protons, the lower number, is 92. We'll set that equal to 2, which is our protons for helium, plus our unknown number of protons, which I'll call y. We can subtract 2 from both sides to solve for y. Therefore, our y is 92 minus 2, or 90. Therefore, our missing product will have a mass of 234 and a number of protons of 90. If we go to this section of the periodic table, we'll recognize that element number 90 is thorium, Th. Therefore, the correct symbol of that missing product is 23490 thorium. Here's another example of a missing product. We can check the mass and check the protons. Our mass on the left says 15, and our mass on the right also says 15, and we'll still have to say plus x. If I want to solve for x, I'll subtract 15 from both sides. This will leave me with an x of 0, which means whatever I'm going to get will have no mass at all. Now I'll check my protons. If I have an 8 on the left and a 7 on the right, I can set up the equation to say 8 equals 7 plus x. Then I subtract 7 from both sides, giving me an x of 1. So, somewhat confusingly, I do have what appears to be a proton, but has no mass. We know that's actually impossible, because protons always have a mass of 1 when you're doing these sorts of reactions. However, some results can look like a proton with no mass. We're going to write 0, 1 for the missing particle, but instead of writing a proton or neutron or any ordinary particle that we're used to, we're going to write the Greek letter beta. This Greek letter beta with a 0, 1 represents a positron. This is not really a proton, but rather the antiparticle to the electron. We call this an antiparticle to an electron because if you place a positron with an electron, they will destroy each other. An electron is oftentimes written in these sorts of reactions also with a beta symbol, but it says 0, negative 1 rather than 0, 1. This is not really a negative proton, this is actually an electron. These are also sometimes just called collectively beta particles. However, our answer for this question is this positron, this 0, 1 beta. Here we'll do a slightly more complex example. Now our job is to find the missing reactant on the left. So we'll have an unknown mass and an unknown number of protons. On the left we have that unknown mass of the missing reactant plus 1 from this next symbol. The symbol says lowercase n 1 0. This symbol represents a neutron. Notice it has 1 mass, but no protons. We'll set this equal to what's on the right side. We'll just look at the mass for now, and we'll have 144 from the barium, plus 89 from the krypton, plus 3 neutrons. Since each neutron has a mass of 1, and there are 3 of them, we'll say plus 3. We'll end up with 236 on the right equals x plus 1 on the left. Then we subtract 1 from both sides. 236 minus 1 will give us a mass of 235. Now we'll look at the number of protons. On the left, we have some unknown number of protons from our missing reactant. Our neutrons have no protons at all, so we don't have to include those in the proton equation. Then we have 56 on the right from barium, 36 on the right from krypton, and then none from our neutrons. We add these together and we get a total of 92. Therefore, our symbol will be 235 as the mass, 92 as the protons, and we can see that element number 92 in this section of the table is uranium. Therefore, our missing reactant is 235, 92 uranium. So this is how you find the missing pieces of a radioactive equation. Thank you for watching, and we'll see you again another time.